do today is that I'll talk about Kundt structures. So they represent a G-structure approach to Kundt spacetimes. And so that's my goal, to get to there. But before I get there, I just want to give some background material. So here's the general overview of the talk. I'll be talking about a little about scalar curvature invariance and algebraic classification. And then I'll be talking a little about Kundt spacetimes. So Kundt spacetimes, they are very closely related to questions about scalar invariance. And then I'll also discuss a little about nil-killing vector fields. They represent the infinitesimal automorphisms of the G structures, or the Kundt structures. And they're important to scalar curvature invariance as well. So lastly, I'll be getting to Kundt structures, where I'll also share a couple of results concerning them. So first, if I have a pseudo-Riemannian manifold, then the scalar curvature invariance, they're all expressions which are obtainable as contractions of the curvature tensor and its covariant derivatives. Here are some examples. And these behave rather strongly in the Riemannian signature. For instance, the scalar curvature invariance, they separate orbits of metrics, and they vanish if and only if the metric is flat. And constancy of all the scalar curvature invariance is the same as local homogeneity. But all these statements are false in Lorentzian signature. Pretty naturally, they are false because we have null directions. What we see, what's been proven by Coley and Hervik and many others, is that all this behavior, which is exotic in the Lorentzian signature concerning the scalar curvature invariance, is contained in the Kundt class of spacetimes. So let me get to the definition of Kundt spacetimes here. So a spacetime is Kundt if it admits a null vector field K, which is geodesic, twist-free, divergence-free, and shear-free. Here's the list of conditions. And it turns out that you can put any such a Kundt metric in canonical form, or not canonical, but coordinate form, in a natural coordinate form, such that the transverse part here is independent of the V coordinate, where the V coordinate is along the null congruence K. So here are the results that are important about Kundt spacetimes and scalar curvature invariance in 3 and 4D by Coley and Hervik and a group of people. So if we have a Lorentzian manifold of dimension 3 or 4, then you can leave the orbit of the metric whilst preserving the SBIs only when the metric is Kundt. So this implies that the metric is Kundt. And if a spacetime has constant scalar curvature invariance, then this is branches into two classes. Either the spacetime has to be locally homogeneous or it has to be Kundt. So this shows why Kundt spacetimes are important when it comes to scalar curvature invariance. Why are these facts true? Well, in order to kind of explain how it works, we have to talk a little about boost weight, algebraic boost weight classification. So first, let me fix a null frame. In terms of a null frame, or actually just in terms of a null vector K, I can perform a boost order classification of tensors. So let me just show how that works for a tensor rank 2. So what you do is that you associate to the frame elements K, L, and Mi weights given by K having weight -1, L having weight +1, and Mi having weight 0. If you want to talk about the boost order classification of a rank 2 tensor, let's say, what you do is that you associate it to the basis elements of rank 2 tensors weights, which are simply given as the sum of the frame element weights. So KK has weight -2, KMI has weight -1, KL has weight 0, and so on. MI/MJ has weight 0, LMI has weight 1, LL has weight 2, and so on. So the boost order of a tensor is defined as the highest boost weight of a basis element with non-vanishing coefficient. Let me show you an example of this. Take a symmetric rank 2 tensor T. If we look at the first frame basis elements here, KL, MI/MJ, they have boost weight 0. So these represent boost weight 0 elements, while this guy here, KMI, has boost weight -1, and this guy here has boost weight -2. So we see that the highest boost weight with non-zero coefficient has boost weight 0. Therefore, the tensor T has boost order 0. So why is this important for scalar curvature invariance? Well, it's really when we're in an algebraically special situation that we can have degeneracy in scalar invariance. Because if we have a tensor T and it has boost order less or equal to 0, then its scalar curvature invariance, or it's just a scalar invariance, arbitrary full traces of the tensor, they only depend on the boost weight 0 coefficients. So let's see about this example here. Well, this means that all arbitrary traces of T, scalar invariance, they only depend on C, the coefficient C here, and Dij. There's no dependence on EI and no dependence on F. So we're free to change this part of the tensor without actually changing the scalar invariance. So this gives a hint as to how it works when it comes to curvature invariance. So first, a little standard notation. We say that a tensor is of type 2 with respect to a null vector k if it's of boost order less or equal to 0, and we say it's of type 3 if it's of boost order less or equal to -1. So this terminology is the same as the one in Petrov classification, and indeed this type of algebraic classification is the same as the Petrov classification for the wild tensor in restricted to dimension 4. So what about Kundt spacetimes? Why do they behave in such a way that you have degeneracies in the invariance? Well, it is this fact that when you have a degenerate Kundt spacetime, then the curvature and its covariant derivative is of type 2, meaning that the curvature tensor has a boost weight 0 part, boost weight -1 part, and so on and so forth, but no positive boost weight parts. And the basic reason for this is that for Kundt spacetimes, because of this special null congruence, which is twist-free, geodesic, shear-free, and divergence-free, we can find a frame such that the Christoffel symbols, they vanish for strictly positive boost weights. So this is inherited when we go up to the curvature tensors as well, under some conditions. So the exotic properties of the curvature invariance, scalar curvature invariance in Lorentzian signature are really due to that the scalar curvature invariance only depend upon the boost weight 0 part of the curvature. We're free to change the rest of the curvature without altering the scalar curvature invariance. And as long as this part is constant, this boost weight 0 part is constant, then we have a Lorentzian manifold with constant scalar curvature invariance. But the rest, the negative boost weight parts, they can behave wildly. So we don't necessarily have to have local homogeneity. So last of the background part is that I want to talk a little about nil-killing vector fields. So first, let me just rephrase this condition of being Kundt. So a Lorentzian manifold is Kundt if and only if there exists a twist-free null vector k, such that the Lie derivative of the metric g with respect to k is of type 3 with respect to k. So this is just reformulated within this algebraic classification formalism. Okay, so what we do is that we try to extend these vector fields k, Kundt vector fields, in order to create a Lie algebra. So we take the vector fields x such that the Lie derivative of the metric is of type 3 with respect to this null vector field k, and that preserve the line of k. And what you can see is that this constitutes a Lie algebra. And the vector fields within this Lie algebra, those we refer to as nil-killing vector fields. Why nil-killing? Well, because this condition here, LXG type 3, is really the same as saying that Lx of G as an operator is nilpotent. So what's the motivation for looking at nil-killing vector fields? Well, local homogeneous spacetimes, they can be characterized in terms of having transitive collections of killing vector fields, locally transitive. So one wants to have a similar characterization of Lorentzian manifolds with constant scalar curvature invariance. And the hope is that these nil-killing vector fields can be used in order to obtain such a characterization. And indeed, there's been some positive results in that direction. You can find sufficient conditions for a nil-killing vector fields to preserve invariance. So these nil-killing vector fields, they constitute a generalization, both of the Kundt vector fields, but also of killing vector fields. So that's why we hope that they're kind of special when it comes to studying the scalar curvature invariance. But now let me talk about the Kundt structures. So the Kundt structures are a type of G structure that have nil-killing vector fields as infinitesimal automorphisms. And it turns out that we can use them as a framework for studying Kundt spacetimes. So this is why I wanted to talk a little about Kundt spacetimes, just to say why it's nice to talk about Kundt structures as well. So first, what's a G structure? If we take a Lie group G of GLN, and M is some manifold of dimension n, then a G structure is a sub-principal bundle of the frame bundle. So for us, we need to define a Lie group Gn, which will be used in our construction. So what I do is I fix the standard basis of Rn, and I fit Rn with the natural Minkowski metric here. And to keep with standard notation, I let K be E1, L be E2, and Mi be E2 plus I. And now I define Gn to be the collection or Lie group of transformations F, such that F preserves the line of K here, and such that the Minkowski metric is pulled back to something which differs from the Minkowski metric only by a type 3 tensor. So note that this condition here is similar to what a Kundt vector field satisfies and what the nil-killing vector fields satisfy. So in terms of a matrix, we have an expression here of the Gn group. So we can write in terms of such a matrix here, where A and B are arbitrary numbers, and C is some vector, and D is a vector, which are arbitrary, and A is a orthogonal matrix. So we see that the elements of Gn really partially preserve the metric, the Minkowski metric. So let's suppose that we have a Gn structure. Due to the fact that the Gn transformations preserve the line of K, then we have an intrinsic distribution little lambda. And due to the fact that the orthogonal complement is also preserved by the elements of Gn, this gives rise to a distribution big lambda. And these distributions are of dimension 1 and codimension 1 respectively, and they constitute a filtration of the vector space of the tangent plane. Because of this filtration, the Gn structures, they give rise to an intrinsic classification of tensors, just like the boost weight classification we discussed before. And because of the nature of the structure group, Gn, this allows us to take, in an invariant way, full traces of type 2 tensors. So Gn structures give algebraic classification, and they give the ability to take full traces. So somehow they're important for studying invariance of algebraically special tensors. So the Gn structure have a natural class of Lorentzian metrics associated with them. What we can do is that we can take a look at the sim n-2 group, which are the orthogonal transformations that preserve K. And we say that a metric is compatible with a GN structure if it's obtainable as a reduction down to sim n minus 2. So what does this have to do with Kundt spacetimes? Well, it turns out that at first that if we fix a metric G of this GN structure, then the infinitesimal automorphisms of the GN structure are exactly the same as the nil-Killing vector fields of G with respect to this distribution little lambda. Moreover, we have a characterization of connections belonging to P. They are the ones that preserve the filtration and that bring any metric belonging to the GN structure to a tensor of type 3. So we have this following equivalent formulation. If we fix a GN structure with distributions lambda and big lambda, then the following are equivalent. Big lambda is integrable, and little lambda contains local infinitesimal automorphisms of P, if and only if all the metrics that are compatible with P are Kundt with respect to this null congruence lambda. So this is why they call these types of GN structures are called Kundt structures, because all their compatible metrics are Kundt. So lastly, let me share two results. The one result is a classification of when a GN structure is Kundt. It says that a GN structure is Kundt if and only if it admits a torsion-free connection. That is, if and only if its intrinsic torsion is 0. If you take a look at the torsion part of the Spencer cohomology, you can see that this is also if and only if there exists a connection whose torsion is algebraically of type 2. It might also be noted that that a torsion-free connection belonging to the GN structure doesn't necessarily have to be a metric connection, because the curvature tensor doesn't necessarily have to have skew symmetry in the endomorphism part. Okay, so the last result I want to share is that if you do have a torsion-free connection belonging to a Kundt structure, then its curvature is automatically of type 2. Its curvature tensor is automatically of type 2. So this allows us to take invariance of such curvature tensors for the GN structure or the Kundt structure. So we can talk about invariance of connections in a wider sense than in the pseudo-Riemannian setting. Thanks a lot for listening. I believe I went a little over time. I'm sorry.